So in the last video we discussed about the construction of the velocity diagram by using the Klein's method. So with the help of this method we successfully drew the velocity diagram for this slider crank mechanism, and by using the similar triangle law or theorem for the uh, for the constructed velocity diagram and the one which is obtained by using the relative velocity method, we find out some relations to find out the velocity of different points of the slider crank mechanism. Now in today's lecture we will use the Klein's construction method to find out the acceleration of the single slider crank mechanism which is moving with constant omega and zero angular acceleration. So this is the slider crank mechanism, basic slider crank mechanism, which is having 4 links, 3 turning pairs and 1 prismatic pair. So this was the velocity triangle which we have drawn with the help of the Klein's construction method. Now in order to draw the acceleration diagram, let us first draw the acceleration diagram for this slider crank mechanism using the relative using the normal method. Now so for to draw the acceleration diagram, so first of all let us consider this point B. We can draw its acceleration diagram with respect to point A and with respect to point C. So the point, let me make some findings with respect to magnitude. Okay, so we will first find out the acceleration of point B with respect to A. So there will be two acceleration, one will be the radial one and another will be the tangential one. This radial one can be given as VBA or rather VBA square by the distance AB, and this can be calculated as alpha into AB. Since alpha is taken to be as 0, so this vector will get 0. So we will only be getting the radial component of the acceleration for the point B with respect to A. And what would be its direction? Its direction will be from B to A. So we will put or lift this vector, this will be the possible direction, and we will lift this vector from here in order to draw the acceleration diagram. Let me take this vector, we will draw it for example like this. So this will be the radial component of acceleration, this will be the radial component of acceleration B with respect to point A, and it is with respect to the point A. So this will represent the point B dash, since there is no tangential component of the acceleration. Now to calculate the acceleration of B with respect to point C, we will write it here. Let me erase this diagram from here and I will draw it here. So this is the acceleration of point B with respect to A. This is the acceleration, radial acceleration of B with respect to A. This is A dash point, this is B dash point. Next we can also find out the acceleration of B with respect to C. So here we will have a radial component of B with respect to C, which can be given as VBC square divided by BC, and a tangential component of acceleration, for example alpha BC into distance BC. Now here, with the help of velocity diagram which we had already learned to draw, we can calculate the radial component of acceleration, but the tangential component of the acceleration is not known to us. And what would be the direction? The direction of the acceleration will be from point C to B, just like the earlier one, the direction was from B to A. Now to take this vector, and we'll draw a parallel vector from this end B in this direction, so this will represent the radial acceleration of point B with respect to C. Since the magnitude is known, so its length is decided. The tangential component of the B with respect to C, it can be drawn by putting a perpendicular on a link B, but its direction is not known, so we will draw a perpendicular or a similar vector like this. We will put it here, lift it from there, and will draw a vector like, just a minute here. Okay, now the another point is the point C, whose acceleration we need to calculate. Now this C will move in this particular direction only. The location of the C or the slider is such that it is bound to move in this direction only, since we are providing omega in this direction. So there will be only one with respect to, we are finding it with respect to A, and there will be an acceleration AC. Now to draw it, let us put this vector from here with respect to A. So we have to begin from here, and we'll draw a parallel line. So wherever the point these two lines will meet, that will give us the point C dash. So this is the velocity, this is the acceleration diagram for this slider crank mechanism. This is the acceleration diagram for the slider crank mechanism. Okay, where this portion represents this one, tangential component of C, this is radial component of B with respect to C, this is radial component of B with respect to A, and this will represent the acceleration of slider C with respect to A. So this is the acceleration diagram for the slider crank mechanism. Okay, now according to Klein, he states that in order to get the acceleration diagram by using the Klein's method, we need to rotate this particular acceleration diagram by 180 degree. Since we need to rotate it by 180 degree, so the positions, or it does not matter whether we rotate it in anti-clockwise direction or in the clockwise direction. Okay, so we have to rotate this diagram by 180 degrees. So to rotate it by 180 degree, let me draw the new acceleration diagram here. First I will rotate this line, so it will be like this from A to C. Then from point C we have this tangential acceleration component. I will draw it first like this. Then we have, from it we have the radial component of B with respect to C. Then we will try to draw it like this, and then we have this radial component of B with respect to A. So we will connect it here. So if we rotate it, it will look like this. So this is the point A dash, this is the point C dash, this is the point B dash, this is the point B dash. Okay, this is the point B dash. So this represents the radial let me take some other color. This will represent the radial component of B with respect to A. This will represent the acceleration of C. This will represent the tangential component of point C with respect to B, and this will represent the radial component of B with respect to C. So this is the acceleration diagram which is obtained for the analysis of Klein's construction. Now, in order to draw the acceleration diagram by using the graphical method of the Klein's, so for that let me redraw this ladder crank mechanism in a clean way for the better understanding. So let this is the this represents the link CB, this is the link AB. Here we have a slider, this is turning pair, here we have turning pair, here we have a turning pair, and here we have a prismatic pair. Prismatic pair, and this is connected, this is fixed. So according to Klein's, what would be the velocity diagram? To draw the velocity diagram, draw a line perpendicular to this link, then extend this line wherever these two will meet. That will give us a point. For example, that point is P, this point was B, this point was A, and this point was C. So this is the velocity diagram. Now in order to draw the acceleration diagram, so according to Klein's method, we need to draw two circles. For the first circle, let me write it here. First circle, take PB as radius. Okay, take PB as radius, and draw a circle. Let me take some other color. Draw a circle. PB as radius and draw a circle. So by taking PB as radius, let me draw a circle. So this will be the possible circle by taking PB as the radius. This will be the center of the circle. Now for the second circle, second circle, take BC as diameter and draw a circle. So let me take a circle. So here BC is the diameter. So that this is the circle. Fine. So this is the second circle. Okay, now the third step is, this is the first step. Okay, this is the second step. This is the first step, second step, third step. Now mark points, where two circles are meeting and join them with a line extending to link AB. So first mark the points. This is the one point, this is the another point. Now join these two points with the help of a straight line and extend that line to link AC. This is AC, link AC. Link AC. Now we will get two more points, one where this line is cutting AC and another point locate on BC. So this is the another point. Okay, what is the step 4? In the fourth step, locate a point on BC where the extended line is cutting it. So mark this point. Now just join these marked points. Let me call it as point R and it is, for example, S. Now join these points with the help of lines. Just join these lines. So this new area, which is represented by A, B, R and S, represents the acceleration diagram. This represents the acceleration diagram. So we will apply the similarity law between ABRS, this one, and the one which was obtained by using the normal graphical method and was again rotated by 180 degree. So this one, so we will apply the similarity law between this 1 and 2. Now applying the similarity law, we can write that AC, this one AC divided by this length AS is equal to A tangential CB divided by this length RS equal to A radial BC divided by this length, which is RB, and A radial BA divided by this length AB. So with the help of similarity theorem, we can find out this mathematical equation. Since we know the value of omega, and we know the value of omega which is given to us, and there is no tangential component of the acceleration, so we know the value of the radial component of r of b with respect to a. So this component is known to us. This length is also known to us. This length is also known to us. So this factor represents the omega square. This represents the omega square. How? Let me expand it. So radial component of b with respect to a, it can be given as by this, and it is further divided by ab. So this will become vba square divided by ab square, which is nothing but omega. Okay, so by using this we can calculate AC, or acceleration of C, as AS into omega square, the tangential component of C with respect to B as RS omega square, and radial component of B with respect to C as, this is radial component of C, this is radial component of C with respect to B, this is CB. This has to be B. Okay, this is B with respect to C, this is B with respect to C, so this is BC. This is BC, this is BC. Okay, so we can also calculate the radial component of B with respect to C as RB into omega square. So by using these relationships, we can calculate the acceleration of different points on the slider crank mechanism. I hope these steps are clear to you. So initially we did the Klein's construction method to draw the velocity, to find out the velocity. This is the diagram. So, and today we completed to find out the accelerations and its velocity diagram for using the Klein's construction method. I hope it is clear to you all. Okay, thank you.